Okay, welcome back. So today is the first review session for exam 3. So it's a good time for you to make mistakes and to ask questions. Oh, I just restarted iClicker. So make sure if you log in into the earlier one, you may have to log into iClicker again. So just like that. Any question? All right. So no question. What topic should we cover today? I guess we can go through the equation sheet. We can either do polarization or we can do what listed on the equation sheet. Up to you. Or you can ask me any question that you have. Yeah. What is your name? Kayla. Could you please, I'm trying to listen to one of your friends. Yeah. What is a flow chart? Yeah, sorry. Sorry, I'm just being a jerk. Yeah. If you want me to make that thing, I can, but not right now. I'm busy. I'm busy teaching right now. But I'll prepare. I think one of your friends asked for an Excel sheet that you can put your grades. I can also do that. But the thing is, there are some adjustment, right? The formula will be complex. And then I guarantee you that the Excel sheet will be wrong. Because we may have extra credits in the future, and then the Excel sheet needs to be modified. I can prepare that, but don't, it's my advice to you, just don't follow Canvas grade. I've said that many times because it's not flexible enough for what we want to do here. We use many webwares or apps, and you will get the grades. You will see your grades weekly. And then Canvas gradebook, that includes the extra credit. I think many of you get 0.13. It will not be 0.13 when you see the weekly gradebook updates. So if you miss the announcement, we have an extra credit. It's worth 5 points. Initially, I put 2 points because I copy the policy from the instructor of the other section who has been teaching this class far longer than me. And his exam is based on 40 points. So 2 out of 40 is equal to 5 out of 100. So that's an important missing information right there. Yeah, Ashley? I had a question about grade, like the grade book. Uh-huh. Some of the survey videos from the beginning semester are graded. Yeah, sorry. It's on me. I know I should have graded that thing long time ago. If you want that thing to be graded, you can email me. I like it. So when somebody email me, sometimes I use that video for a different purpose. Like when somebody email me with questions, I like to see, or meaning like understand more where this person or this student comes from. I use that thing. Also, in the future, if you ask me to write a letter for you, typically I start by watching those videos before and after, and then I can personalize the letter. Yeah. Peyton. Is that good? Sorry. Yeah. But it will be graded, don't worry. It's really easy. I just need to binge watch those videos. Yeah, go ahead. It's going to exam 2. Any other question? How about question about exam 3? Like, you guys ready? Okay. What should we do? I guess we can come up with, I guess we can review polarization again, or you guys think polarization is easy? So let me come up with a problem. Well, the first one is, if you, let's say we have light from sunlight, so meaning the polarization is scrambled, so this is unpolarized. Maybe there will be delay, but that's okay. Unpolarized light, and then I introduce a filter or polarizer. What is, so, and then the intensity of the input is I input. What is the intensity of the light that comes out of polarizer? So, okay, in terms of polarization axis, let's say is a vertical, and then the question is, what is the intensity of the light that coming out of the polarizer? One is I in, B half I in, C So I'm curious whether you can answer this question. Shouldn't take you too much time. All right, 15 more seconds. 10, 5, 4, 3, 2, 1. Okay. So again, this is a good place for you to make mistakes. What is the answer? The answer is B. What formula that you should use? The formula is, or the law is Malus' law, or Malus' law. I think Malus' law. So I output is equal to I input times cosine square phi. Okay. But the, okay, so, and then what is this phi? Is this phi? Yeah, phi. Or if you are Greek, you pronounce it phi. Phi is the angle between the polarization axis and each of this. Okay. So because unpolarized light doesn't have a defined polarization axis, so it has all angles. So basically I out is equal to the mean or the average of I in times cosine square phi. And then the mean of this part is I input times the mean of cosine square phi. Okay. You can either memorize this, that cosine square phi is equal to 1/2, or one way to remember it is, I asked you like 2 lectures ago, many of you knows that sine square phi plus cosine square phi is equal to 1. And these two functions are shifted. They are symmetric but shifted by 90 degrees. So they are identical. So in theory, so this one is equal to, so cosine phi, the average of cosine square phi is equal to 1/2. So using this value, the answer is in divided by 2. Okay. Any question? Okay. And then let's put d is equal to 0. And then next, we did this last time, so I'm just checking whether you guys, whether I thought, whether there was any information flow from me to you. So, and then we put another polarizer. I think your textbook used the term analyzer, which is basically, in reality, they are identical optical component. And this one, phi is equal to, or this one is horizontal, this is vertical. So I'll give you the number. So the question is right now, what is the intensity of light after the second polarizer? We did this on Monday, okay? One. Which one? Ah, sorry. Yeah, thank you. So this is the problem, not the one on your iClicker. So option E is 0. Ten more seconds. 5, 4, 3, 2, 1. Okay, good. So that's the results. The answer is E. So using this one, so at this point, the intensity of light is I input, and in the exam, I may use I naught. I will use I plan to use the same symbol as in your notes. And then after the first polarizer, it becomes half. And then this one, the intensity is I in divided by 2. So the input of the second polarizer, which is I input divided by 2 times cosine square times 90 degrees. And this one is equal to 0. So the intensity is equal to 0. Okay. Yeah. Madeline, yeah. Yeah, so the angle is the angle between consecutive polarizer. Or here between the input lights. The reason why the angle is between consecutive polarizer is after the previous polarizer, the angle is defined by the polarization angle of the first polarizer. So this angle here is the angle between this angle and this angle. Okay. All right, so and then let me expand a little bit. Let's say I rotate the last polarizer. So still two polarizer, the input is unpolarized light. If this is too easy for you, feel free to come up with a question and we can do it as a class. So let's say the angle, the second angle, or if you want to label this, by 1 difference with the angle difference between 1 and 2 is equal to 45 degrees. Okay. So what is the intensity after the second polarizer? Okay, let me erase this, change it to zoom, and then good. Good. You guys are fast. 15 more seconds. Five more seconds. 3, 2, 1. So good. So I don't think I need to say much. Basically using Malus law and then cosine, but be careful. Okay, so let me just do it explicitly. Again, the input is still the same. Okay, this is the input of the second polarizer, not the input of your optical device. And then times cosine square. And please check this one. This is from the number in that table is from what I learned when I was a high school student. Forget to check. Is this correct? Yeah. And then this one, is this what how you learn it or no? Yeah. Something like that. Okay. Yeah. And then this one is anyway. I don't want to. Yeah. You can either use your calculator or check with me. Email me if that's how you learn it when you were in high school. So okay. So this one is cosine square for 45 degree. And this one is equal to 1 over square root of 2 square. Please check that. This one I made a typo, should be divided by 2. So equal to 1/2. So equal to I input divided by 4. So the answer is C. Good. And then on the exam, I can put infinite number of polarizer, let's say. That's a fair game. Yeah, Sophia. This one, yeah. So the input is unpolarized light from the sun or any source, any non-coherent source. So basically, if you want to plot the distribution, this is angle. It's a uniform distribution from 0 to 360 degrees. So all of these are the values of phi. So you need to sum all of those phi. So basically, we need to find the average of the phi. To be more specific, the average of cosine square phi. So, and then mathematically, we know that cosine square, the average of cosine square phi is equal to 1/2. What is the average of cosine phi? Good. Who said 0? Good. Okay. What is the average of sine square phi? Huh? Yeah, good. because they are the same, it has the same values, but shifted by 90 degrees. So this is sine, this is cosine. Sorry. I know at this point I'm right, and then like this, right? And then for this is sine or cosine, this is cosine and sine. And this is the cosine square phi or sine square phi. So it will be something like that. That's for cosine. For sine, it will be like this. So it's the area under the curve is the same, they're just shifted. For the exam, you just need to know this one. And as long as you know how to use your calculator, be careful that this one is, the angle that you put is in degree or radian, then you should be fine. And then on the exam, don't assume that the input is unpolarized. It could be already polarized. Just read the question carefully. Based on the statistics, most of you finish the exam early. So just take 10 more minutes, like read the question carefully. Yeah. Yeah. Which is basically like this one, right? So you know how to do it. But instead of 1/2, right? So this is basically one example of the scenario that you're asking. The light is already polarized. Ignore the left half of the whiteboard, and this one is what you're asking. Oh, I will tell you, or yeah, I will tell you that a polarized light hits a polarizer at an angle alpha. 30 degrees, 45 degrees, 62.5, any angles. As long as you know this is the formula, which is not there, so I need to add the formula to the formula sheet. Somebody asked me this morning whether all of the formula will be useful on the exam. The answer is, of course not. One of the goals of education is to teach you or to train you to be able to select the information that you need to move forward, to make a decision. So don't cross equation. Oh, this one has been used. This one has been used. This one I haven't used this one. I will use this equation. That's not the case. Any other requests? How comfortable are you with right-hand rules? Easy? Yeah. Lenz's law. Maybe any question in the study guides? Because that thing is kind of involved. I can come up with a scenario. What is a good one? Because in class we did this, right? This is, I think, north. Oh, can I take a step back since it involved magnets? I really enjoy reading your extra credit assignment. No joke. I do read those submissions. So many of you think that the last problem is confusing. So this one is exam 2. Right? There is this problem of, this is similar to Faraday's motor. Just because Faraday did this, it doesn't mean that the material is from exam 3. But this is exam 2. This is basically a cross-section of Faraday's motor. And then I don't remember exactly, but I think this one is positive and this one is negative. And the way I draw it is, so positive, negative, and negative, right? So this means the reason why I put this question is I want to see if you know how to assign the direction of magnetic fields. So basically the direction magnetic field is like this. So the magnetic field is downward. And then second, I wanted to see if you can come up with the direction of the velocity. So B, this, and velocity for positive charge, positive. This one is positive. V is to the right. For negative particle, if you have negative particle, it will be attracted towards the positive electrode. So V, we can label it this. But the magnetic field still point downwards because of the position, the orientation of the magnets. So using this right-hand rules, I don't know, maybe I don't need to use that camera, you can just see me. V point this way, magnetic field point down. Magnetic field is my middle finger, and the force points towards the, what is this? Oh, this is whiteboard, right? Point to the whiteboard. And then this one, V is your pointing finger or index finger. V points down. So it points towards you, but because the charge is negative, then we have to flip. So VB points also to the whiteboard. So both positive and negative at this point will move towards the whiteboard, and the motion of these charges, if you look at the motion from the top, will be clockwise. So that's the answer for the last problem of exam 2. The reason why I'm covering this because many students ask this question, and also it involves right-hand rule. So for Lenz's law, do you have a good question that we should cover? Because we did this in class. Yeah, Sophia. This is velocity, not current. This is positive ions, or negative ions and positive ions. The positive electrode is here, negative electrode is here. Here, on the other side, the negative is here and the positive is here. Because it's a cylinder, like a bowl. I think that's how Faraday did it, on a bowl. All right. So this is what we did. Any other question? So on the exam, well, at least there is one problem that tests your understanding, meaning like all of them test your understanding, but this one is a good problem, let's put it that way. Because otherwise, if the exam is too easy, I will bore you to death. I need to entertain you. And then the exam is graded 14 points out of 15 anyway. So you can still get a perfect score even if you miss the bonus point. Do you? I feel like I'm not I'm not that creative, but okay, let's do the same problem that we did in class. Okay, so this is there is a loop. The loop moves up. So you have a loop of conducting wire, and you move the loop upward in the presence of two permanent magnets. So there is B here. And then a typical question is, what is the direction of the currents? Okay, so first, what is flux? Flux is flux. Unfortunately, this one is not angle, it is flux. Is equal to B times A. And if you move the loop upward, the flux will increase or decrease? Who says it will increase? Nobody. Who says the flux will decrease? Nobody. Okay. Most of it. Good. So because it decreased, then this is somewhat similar to the concept of inertia, but basically nature tried to minimize changes. So in order to minimize the changes, nature tried to generate magnetic fields to minimize the changes of the flux. So the induced magnetic field also points to the right. So this is B induced. Okay. And then if you figure out, so at this point we're using Lenz's law. Okay. We know that if there is a change of flux over time, and you can even have more than one loop, then you will induce, I'm just going to put here, then you will induce an EMF. And then the reason why I put negative sign here, the direction of the induced magnetic field oppose the changes. Okay. So once you know the direction of the induced magnetic field, then you can figure out the direction of the currents. Here, if you look at it from the North Pole, it will be clockwise. If you look at it from the South Pole, it will be counterclockwise. So you have to be careful. You have to read the problem carefully. That's one example. Do you have a better example? At one point, you guys are really good with you have pre-med students have good memory, so that's good, because one of you may be my physician in the future. One time I say that I can also ask questions about experiments, so I'm gonna write that. Write that. I'm gonna. Okay, so remember in one of the lectures I did a jumping ring experiment. Okay. So I may write a question that is based on that experiment, but instead of telling you that in the class I did this experiment, I may write something like this. That's good. Good enough. So there is a coil. So this is a coil. And then I put another coil here in free space. And then what happened, and then I may ask, what happened if I close the switch? The question is whether the ring go like attracted towards and I'm gonna say this is a light ring, so gravity is not important. The question is whether the ring will move upward or downward or to the right or to the left. What is the answer? Wait, if I close the switch at this point, if I close the switch, what happened when I close the switch? Sarah. I don't even, there are so many Sarah here. I know one of them typically sits here. Nick, Sarah is not here? Ah, okay. There is Sarah with H, Sarah. People at the back. Yeah, you. What happened here? Why? Huh? Oh, you're trying to figure out. Good. I like that answer. But his answer is correct. Why the ring jumps? Well, first is the flux. Does the flux increase when I close the switch? Increase from 0 to B times A. So at basically there is a step function. There is a step function there. So before, this is before, and this is after up. After. Before magnetic field is 0, area stays the same. And after we close the switch, there is a change, right? So over a short period of time, there is an induced current here. And if, let's say, the magnetic fields point up, then to reduce the point up means like this. Then to reduce the change of flux, then it will induce magnetic field towards the opposite direction. And then what you have is repulsion. This is similar like if you have North Pole, you bring two North Poles of permanent magnets, the field looks the same, right? And we know from experience that if we bring the same poles close to each other, they will repel. So this is the reason why the ring jumps. Yeah, Madeline. Yeah, the easiest thing just to good question. The easiest thing is just to maybe this one is easier. The reason why I draw the other lines is to show you that it looks similar to permanent magnets. But this one also have the same magnetic field lines. And since we know from our experience, if the magnetic field lines points towards opposite direction, they repel. This is just easier for me. Perhaps for you, this one is easier. Yeah, Armand Hernandez. Yes. Oh, so this one is because okay, so first, I see. Good. No. I thought that I didn't, yeah. So This one is correct right now. I just gave one example that, and it's easier to think of a system if the arrow points up, but I was being careless with the position of the battery. Okay. Oh, it's always jump. Always to minimize the change of flux. Okay, Sophia. Oh, okay, good. The direction of the induced magnetic field always opposes the change of flux. Okay. Don't worry. Right now, the point of this question is that the ring will jump because of Lenz's law. That's the point of this. Don't worry too much about the direction of whether it goes up or goes down, but they will repel. So the B induced will, if this one points up, then the induced magnetic field will point down. If this one point down, then the induced magnetic field will point in the opposite direction because of Lenz's law. Any other question? Yeah. Okay, first, the direction of the magnetic field depends on the, okay, so let's do it, let's build the problem one step at a time. Okay. So the direction of the magnetic field depends on the currents. Okay. Right. And currents depends on the direction of the battery. Okay. And then you can use a loop or a shape. It doesn't have to be a circle. It can be, let's say, a square, but it has to be a closed loop, meaning you cannot just bring a wire. Then this one will generate the flux, will generate magnetic field to oppose the change of flux. Okay. Since the external flux point down, this one will induce magnetic field that points up. Basically, it needs to, since the flux points down and it increases, then the loop will generate magnetic field that points up, and then it will repel. Okay. What time is it now? Oh, 5 more minutes. If there is no other question, we can finish early. No questions? Let's look at the equation sheet. Make sure you know right-hand rules, including we added a new one, which is the direction of the propagation. So that's one. And you know how to do radiation pressure. And I will tell you whether the material is a perfect absorber and perfect reflector. Okay? If there is no more, Eva. Yeah. Direction of propagation. Is this good enough? Oh, so my advice, if you want to ask question, maybe you can send me the problems beforehand. So the problem will be at higher quality than this one. I have question and then so it could be, like here maybe this one is y-axis, this one is b, this is actually z-axis, and I can ask you, let's say the electric field is polarized along the y-axis and the magnetic field is polarized along plus z-axis. Where is the direction of the propagation? Something like that. And then you, last question. I think last time, the day before the second review, so maybe tomorrow. Is that good? It will be the same file, by the way. So the file name is the same, everything the same. All right, I'll see you on Friday. What's up? Yeah.
Since that would be the first polarizer that we're using in terms of.
In the end, what matters is